My name is Sina Mahadran,
Hi, I'm Arshdeep Dhillon.
and this is our project, High Dimensional Visual Embedding for Language Line Perception. This is for EE641 at USC. This is the goal of the project. We're basically demonstrating that we can take like a rich visual embedding and encode it into the higher dimension and pass that through an LLM to resolve some sort of spatial understanding from that image. So we take an image, pass it to the decoder, we perform some sort of projection, and pass that to the LLM, and we output a sequence of discrete moves. This is the pipeline that we've generated. We start from a data set here, and we pass that through the encoder, as we mentioned before, the image embedding in the decoder, and we expect to get the solution back. That can be the exact solution or the valid solution. This
So,
is the data set.
yeah, we're using 5 by 5, 4 by 4, and 7 by 7 grids. And you can see that the amount of possible solution changes based on the grid size. And the only moves we can do are right and up. So, therefore, the unique solutions that exist for these grids are 20 for the 4 by 4, 70 for the 5 by 5, and 924 for the 7 by 7 grid.
This is the data set generation. So how we basically did this is any path that's adjacent to, or any obstacle, any square that's adjacent to the path has a 70% chance of having a blocker. And if it's farther from that, then it's a 40% chance. And this basically helps us create a more stable training structure where we actually have some sort of a pattern that the model can learn off of. So the left is the original and the right is the fix that we've implemented. And this is just
And
showing the
these
number
are
of variations that we have. So from 0 to 49 is one pattern, but we've got different grids representing that pattern. And then from 50 to 101 is the same thing.
Yeah, so we do have duplicates in our grids, obviously, because these are randomly being generated. And you can see that the smaller the grid size, the more duplicates that are produced. And this was a artifact of us creating many iterations of just to increase our training set. But as you can see, that as we increase the grid size, the randomness kicked in, and the amount of duplicates we had went down drastically.
So we basically ended up picking ResNet instead of visual ImageNet, or the visual transformer. And that's because we just found that we had stronger results while we trained just the raw images. This is just the architecture overview. We ended up having 12 million parameters. Optimal training, we ended up picking 12 million because we found that anything above was just memorizing at that point. This is just trivial, basically explain that there's two paths or more that can be found from the start to the beginning or start to the end. Here are the 4x4 creative solutions, 5x5 creative solutions, 7x7, and these are the results. This is the error analysis.
Yeah, so most of our issues with the results were us hitting a wall, basically the model not being able to predict a correct path through the maze. And we had very minimal invalid solutions, which were out of bounds or wrong tokens or didn't reach the goal. Well, didn't reach the goal is it's very difficult for the model to actually predict right moves and not reach the goal, but most likely it is we would just hit a wall. So that meant that it didn't actually understand the topography of the map of the grid. Sorry.
And these are our conclusions. We found that ResNet performed much better, and our model understood true spatial reasoning, and that we of course need validation based evaluation to produce multiple task solutions.